Okay, thank you. I'm Shota Yamanaka from Yahoo Japan Research. In this study, we investigate the effects of gap between touch UI items on user performance. When we operate touch screens, pointing to a small target is difficult. And in addition, if the intended target and unwanted targets are densely arranged, we accidentally tap a neighboring item. So we test how gap affects user performance. To avoid such accidental taps, some research and guidelines recommend using large targets and large gaps. For example, target size should be larger than 70 millimeters, and the gap should be larger than 3 millimeters. But these guidelines are for large touch screens, like ATM terminals. So these guidelines cannot be directly applied to GUI designs for smartphones and tablets. Last year, we reported the results of how target size and gap affect user performance in mobile HCI and ISS. In these studies, participants must tap a green target, and if they tap pink distractors, they must wait a penalty time to be over. But our limitation was that these experiments were very controlled, because we used a middle-sized tablet which was set on a flat table, and index finger was used, so the participants could tap the target very precisely. In addition, these were conventional laboratory experiments. Only university students participated. So to solve these limitations, we conducted 4 experiments in current study. The first difference is that we use smartphones, because smartphone is the most common device to use touch screens. Because we want to study the practical gap for touch UIs, so we instructed the participants to operate the smartphone in the one-handed thumb style. This is the most common posture for smartphone operations. In addition, we conducted both laboratory experiments and crowdsourcing experiments. Crowdsourcing is a good choice to study the practical touch pointing performance, because the results show more realistic data performed by actual users, which are not limited to university students. And a large number of participants will show a stronger statistical power. Okay, I explain 4 experiments. In this laboratory-based 1D task, 12 students joined. The task is tapping the right start bar and then tapping the green target. If they tapped a pink distractor, a penalty time of 3 seconds was added, and after tapping the green target, they must wait the total penalty time to be over. In total, we recorded 1,440 data points. Here we mainly report the task completion time and mean number of taps on distractors in a trial. First, we found no significant main effect of gap on task completion time. The blue chart shows that the task completion time seems to decrease as gap increases, but the effect was less than 10%. And the orange chart shows a clear effect that 0 mm gap shows the greatest number of distractor taps, around 5%. And we observed only few distractor taps where gap was 1 mm and 2 mm. And finally, there were no distractor taps where gap was 4 mm and 8 mm. So in summary, when gap was 4 mm or larger, there were no negative effects of distractors. And we also reported other results such as significant interactions, so please see the paper for more details. Next is the laboratory-based 2D task. This experiment was conducted on the same day as in experiment 1, performed by the same 12 students. In this task, the green target was always surrounded by 8 distractors, so participants must adjust their finger position both on the X and Y axes. The results are similar to those in experiment 1, but we observed a significant main effect of gap on task completion time. The time in 4 mm gap was the shortest, and it was 20% reduction from the 0 mm gap. And the mean number of distractor taps for 0 mm gap was about 7%, and there were no distractor taps in 2 mm or larger. So in summary, when gap was 4 mm or larger, there were no negative effects of distractors. Next, we replicated these two experiments performed by crowd workers. The crowd workers accessed our experiment website by using their own smartphones. And they read the instruction page, go to the questionnaire page, and then go to the experiment page. In the instruction, we asked crowd workers to hold the smartphone in your dominant hand and touch the screen with your thumb, and don't use your non-dominant hand. Then, according to the responses to the questionnaire, the system automatically changed some settings. The important point is the response on screen resolution in DPI. The system scaled the target size and distractor size depending on the DPI. And these are the results. First, the task completion time in 1D task was not significantly affected by gap. But in 2D task, a 4 mm gap showed the shortest time. So the results of task completion time were similar to those in laboratory experiments. However, the numbers of distractor taps were not zero, even if gap was 8 mm. So all pairwise comparisons showed significant differences. Therefore, we cannot determine the minimum gap to eliminate negative effects of distractors. So this is a summary of 4 experiments. A key finding in crowd-based experiments is that we couldn't find the minimum gap to eliminate the negative effects of distractors, because all pairwise comparisons showed significant differences. This point is one of the advantages of crowd-based experiments. That is, the possibility to trigger error operations is very small. Therefore, in laboratory experiments, the distractor tap rates were sometimes 0%. But in crowd-based experiments, distractor taps were observed in all conditions, and statistically significant differences were found for all pairs. However, in the crowd-based experiments, we also found some problems. First is data filtering. In a previous study, Find Later and colleagues used the IQR method to detect outlier data and outlier crowd workers who showed extremely short or extremely long task completion times. But in our study, many older adults joined, and therefore some of them might have low vision. So if those workers carefully performed the pointing tasks, the task completion times would be longer than younger workers. But removing those long time data would be not good, because those results are realistic data by actual older users. Another important point is to detect crowd workers who didn't follow our instruction. In typical research in crowdsourcing, quality screening is necessary. And a common solution is using verifiable questions like don't put a check mark to this question to detect crowd workers who don't read the instruction. But in touch UI experiments, such question-based filtering cannot be used. So to solve this problem, Find Later and colleagues used a smart method to detect crowd workers who didn't follow the instruction. In this touch pointing task, the instruction page shows place the iPad flat on a table. And they compared 3 groups, laboratory participants, crowd workers with this instruction page, and crowd workers without this instruction page. This experimental system recorded touch pointing performance and movements of iPad recorded with acceleration sensors. Of course, the acceleration in the laboratory experiment was almost zero. But in contrast, the acceleration of crowd-based experiment without instruction was very high. And this is because some crowd workers held the iPad when performing the pointing task. And the problem is the result by crowd workers with instruction. 37% of this group showed great acceleration, which means that those crowd workers didn't follow the instruction. So this is a smart method, but this method cannot be used to detect other kinds of cheating. If crowd workers don't follow the instruction, the pointing task can be performed more easily. For example, using index finger or pinky finger allows to perform precise pointing. Also, using a mouse, touchpad, and a trackball is possible by using Bluetooth or USB host cable. And finally, inputting incorrect screen resolution is also a problem, because inputting a larger DPI makes the target size and the gap size larger. To detect these cheating methods, a possible method is this. Some crowdsourcing platform provide video record and upload option. For example, in a platform called UI Scope, task requesters can ask workers to shoot a video during the task. So requesters can check if workers follow the instruction. But a drawback is that this is very time-consuming. In our case, if we check all the videos, it takes 165 hours. And we also have some ideas to avoid inputting incorrect DPIs. One is to ask workers to install native Android apps, which allows to draw targets in physical sizes like inches. But this is more difficult compared with current web page-based experiments. Another idea is to ask workers to measure the physical size of a given circle on screen. For example, if a 100 pixel diameter circle is reported as 10 millimeters, the system can scale the target size. However, this is also difficult for crowd workers. This is an interesting work by Kim and colleagues. Crowd workers are asked to measure the iPhone height and shoot the picture. But the accuracy was 97% on average, which means that there is 3% difference from the actual size on average. So this method is also not completely reliable. So in conclusion, we found some issues in crowd-based touch UI experiments, such as that we cannot check if workers follow the instruction. But if we solve these issues, crowdsourcing is a strong tool for UI evaluation, because crowdsourcing provides diverse participants and statistically stronger results. So we would like to continue using crowdsourcing for touch UI experiments and solve those limitations in the future. Okay, that's all. Thank you for listening.
Thank you. Questions? Any question? So, yeah. So, I mean, you said that you are having some older adults. So, how many? I mean, how many older adults you recruited, or is it from Japan or from outside? I mean, everywhere in the world. And what is their demographics? Yeah. Sorry.
Yeah. We used a platform called Yahoo Crowdsourcing, and that is our company's crowdsourcing. So participants are only limited in Japan.
Okay. And very interestingly is because I'm also living in Japan. So, I mean, older adults usually perform these crowdsourcing tasks. I mean, in Japan. So, I mean, what is their demographics? How age range of the older adults? And I mean, they are younger, old. I mean, 65 to 70 years of old, or more than 75 years of old. So, do you know? I mean, did you check the demographics of these older adults who participated?
You mean
the age.
Performance result for each?
Yeah. So for the crowdsourcing, I mean, you collect the data. So
we didn't analyze the pointing performance results for each, performance results by 20s workers, 30s workers, but in related works, such pointing performance comparison between ages were reported. So,
no, I mean to say that, okay, so of course this is the next step. I mean, I just want to know that what is the age range of the elderly people you got? I mean the crowd workers who participated. So, do you have the statistics that what is the age of them? Age range.
Yeah, that's our future work.
Oh, okay. Got it. Any question? And what is the current, I mean, the immediate future work of this, or do you want to see the more applications of this study? So,
yeah, our next step is to analyze the task variations. So our tasks were very controlled and limited. So, for example, we only used fixed-sized distractors and that were equally offsetted from the target. But in actual and realistic applications, there are various target sizes in different gaps.
Yeah.
So this result is very first step of our long span research project. Yeah.
And did you have anything to consider that if they are moving, not sitting some places? So
like crowdsourcing result. Walking.
Yeah, walking or some other posture.
Yeah, we considered. But so typically crowd workers perform the task in their home. But in Japan. Using smartphones in walking and riding on bicycle is maybe illegal.
Yeah.
So we cannot test such a conditions.
Yeah. Got it. Okay. Okay. Once again, thank speaker. Let's thanks to the speaker.
Thank you so much.
Thank you. Okay. Now the room has many people, so I can introduce myself. My name is Shayan Sir.